Hey, this is Alex Panner, and this is Lab 5, and our main objective was to observe drag force, and using the momentum principle, you get dp over dt equals F net, and which is the sum of all the forces, which in this case is the force of gravity plus the force of drag. So our chief results was, since the force of drag is proportional to speed, the object will fall faster until the magnitude of the force of drag equals the magnitude of the force of gravity, in which the forces will cancel and the object reaches its terminal velocity. So for my video, for my fast falling object, I looked at 19 frames of about that are a 30th of a second, or 0.633 seconds of a basketball falling, and I calibrated it using the ball, and using the center of mass to track position, it starts at the origin and falls in the negative y direction. My second object was a piece of paper, which I did everything the exact same except I used a letter on my shirt to calibrate it, and it was 25 frames long, so because it falls slower, so to be uniform I stopped it at 19. Okay, so first we wanted to compare this to something that does not experience drag. So here is my tracker data, and you can see that the paper falls the slowest and the basketball falls faster, and of course something that doesn't experience drag falls even faster. So we wanted to simulate these models. We wanted to simulate the ball and the paper using VPython. So for my basketball, we have the initial conditions, which the mass of the ball 0.608 kilograms, the initial position and velocity are both 0, and delta t is 1 over 30, which is like the time frames in the video. And then from the momentum principle, we have the F net is equal to the force of gravity plus the force of drag, which we see here. And then from the momentum principle, we can get the ball's position. So this is what this one looks like, the basketball. You can see here. And then for the paper, we did the exact same thing. The only difference is the mass. And that's this is what this one looks like. Okay, so once we did that, we extracted the data, and I graphed them to get these results. And this is my basketball model, and you can see this one pretty accurately represents the model, pretty accurately represents the video tracker data, which the video is blue and the model is red. So that was a pretty good representation. And then for the paper one, you can see this one wasn't quite as good, but it was still fairly accurate, which because the blue is the paper and the red is the simulation. So this one was also a pretty decent representation. And the green line kind of ties in with our what does it mean, which is which model predicts a terminal velocity. And here the green line represents no drag, and you can see that the rate of change, which is the velocity, is increasing as t increases. However, with drag, the slope or velocity tends to a more linear slope, which would be the terminal velocity. This is because as t increases, so does the speed, and the drag force increases. Eventually, the magnitude of the drag will equal the magnitude of the force of gravity, in which the velocity will be constant because F net is equal to 0 because they cancel each other out because they're in the opposite direction. So if you let the simulation run for a long time, you'll get that the terminal velocity is about negative 2.289. And so this kind of goes along with our what if question. And our what if question is, does the object reach a terminal velocity if thrown down with an initial velocity? So first let's look at it. We're going to start it at negative 2.2 and we're going to look at it with no drag. So this is what it looks like with no drag, and you can see it's kind of a curved line, and the actual final velocity is negative 3.5. So that one does not reach a terminal velocity. And for drag force, this is what it looks like. And you can see it's pretty much almost a straight line, and the final velocity is negative 2.28, which is very close to the terminal velocity that I estimated. And that's all.